Good morning, everyone. Well done on making it to the 9 a.m. session. I'm still on Perth time, so for me it's 7 a.m. So the main reason I'm at this session is because I'm giving it. I set 3 alarms this morning, just to be sure. So I set my iPhone, and I set my wife's iPhone alarm. And then, just to be really sure, I had a third alarm. So for that, I ran a LINQPad script. There it is. Hang on, it's not working. Here it is. There it is. I ran this LINQPad script to wake me up in the morning, just in case the iPhone alarm didn't work. I have once had an iPhone alarm fail on me. I missed a flight. And what had happened is I was setting the minutes on it, with your thumb, you flick it down, and I fat-fingered the AM, PM. So I flicked it to PM and it didn't wake me up. So this is my backup. And I thought this was pretty foolproof, because I tested it and it worked when I tested it. But this didn't work this morning. Nothing happened, and it's not what you think. The laptop didn't go to sleep because I disabled that, right? That would have been a rookie error. But what had happened was, when I looked at the laptop this morning, the media player had opened, but instead of playing that song, it had popped up a dialogue asking if I wanted to try groove music, pass, unlimited for 1 month before proceeding. So yesterday, so I gave a soft talk, and some people asked me if I would make up for it by giving an extra hard talk today. And the answer is yes. So I'm going to talk about a problem I had a couple of years ago, writing a new feature for LINQPad and how I solved it. Start with, I made some soft slides, which we won't spend too long with. But I had to make some slides on why I think C#'s still a good language, and a slide on the reach we've got now for C# on the cross-platform and so on. But this is probably the thing I want to spend a bit more time on, which is what makes C# quite unusual, in that most languages, they tend to be either kind of low level or high level or medium level, but C#'s it's got quite a broad reach. So most people, when they start programming, they'll use loops, variables, methods, as most kind of basic possible constructs. And then the other thing, which is pretty much the bread and butter of C# and also of Java, is classes, object orientation. So this is the level that most people are really comfortable at and they work at. But C#'s also, over the years, it's shifted somewhat towards the right, because we have all these other things too, which are very expressive features. So they let you achieve a lot with a little bit of code, right? It takes a while to learn, really get comfortable with using these features, but they do an awful lot with a small amount of code. Now, most people, I would say that they use some of that. They're somewhat comfortable with that. People, though, that have come from a functional programming background, if they go to C#, they'll straight away start with all that stuff on the right. They'll reluctantly use a little bit of the stuff in the middle, classes, object orientation, and they will really try and avoid loops and mutable variables. Now, this is not the end of the story, though, because C#'s also got something right on the edge there, which is the ability to do direct memory manipulation with pointers. And that kind of raises a question like, why do they have that in there? Do we still need it? Is that important? And if you're going to use that, are you also going to use that stuff on the right-hand side? And this comes back to this session, which is that I had a problem, and I ended up needing this whole range. Pointers and direct memory manipulation, you don't often need it, but when you do, it's really, really useful to have. And the great thing about having it in C# is you don't have to go to another language to do that, because how many of you are confident using C++ nowadays? You could bring up, not many, only a few people, right? And the problem is that if you're working in another foreign language, you're very unproductive, and then you don't have all of the good stuff on the right. So having that in C# is great. So we're going to start with this problem I had, and this was in LINQPad, writing LINQPad. So if you're not familiar with it, I'll close that down. We'll start with something like 1 plus 1. You've probably all used LINQPad. So it's like code scratch pad. Bring up another query, and we can put a loop in there. We'll write to 100, dump that out. Now, the way that LINQPad used to work is everything ran in one process. And so the way it would keep your queries isolated is it would put them into separate application domains. And that actually works surprisingly well because the separation you get through app domain boundaries is quite good. But a couple of years ago, I wrote a feature which required that I isolate every query into a separate process. And that feature was the integrated debugger. So now you can single step through your code and watch your variables change. But that means that it has to be running, your code has to be running in its own process. And we can have a look at that and see, go to Task Manager. We'll see it running in there. No, maybe we go to Details now. That's how you do it. Here we are. So there we are. You've got LINQPad host process, and then you've got a user query for each of the queries that are running in there. Right? And the reason there's 3 and not 2 is that LINQPad creates, it speculatively creates another container all warmed up and ready to go. So if I create a new query, it avoids the startup cost. So this created a problem because when I moved from app domain isolation to process isolation, I need a way that the domain queries, the process of that your code's running in, can talk to the LINQPad host process and vice versa. There is a lot of elaborate communication that goes on to make LINQPad work because it's quite a rich environment. So before, I was using technology called .NET remoting. And that works, it's been around since the beginning of C#. It works incredibly well when you're talking between application domains in the same process. Incredibly fast, rich, robust, reliable, no problems at all. But once you start using it to try and talk between processes, it doesn't work so well because now you need to create a communications channel. You can use an interprocess channel or a TCP channel. An interprocess channel uses .NET pipes. TCP, you can use TCP IP if you want. You can even use this to talk to processes on a different machine on the other side of the world. In fact, this is what people did before we had WCF. You would either use remoting or web services as a way to talk between processes. But what I found was that when I switched to doing that, the performance went down, and it would periodically disconnect. And I could not get to the bottom of why, that there seemed to be some bug in the RPC channel. So I thought, well, maybe what I need to do is write my own remoting from scratch. How about that? And I thought, how hard can that possibly be? Now, when it comes to writing your own libraries, sometimes it's a bit easier than it sounds because you only need to write the features that you need. There's a lot of stuff in remoting I didn't need. So I thought about what I did need to be able to call a method in a class in another process, right? And there's a lot of other stuff I don't need. So I started doing that. And then I thought, well, what am I going to build on top of? What's the basic way from one process to talk to another? And that, in Windows, you've got something called pipes, which is a low-level way of doing that. And so I started using pipes. And what I found, pipes, if you use it in a simple way, it works really well. It's fast, reliable. But I was needing to use it in a fairly complicated, asynchronous way. And I could not get it to work at all the way I wanted. So I realized, what if I write my own pipes from scratch? How hard can that be? So I thought, let's do it. So we're going to start by writing our own pipes. And then on top of that, we're going to write our own remoting. And it won't be that much code either. We're going to do it in the simplest way. So to write the pipes, we need something even lower level now to work with. And the thing we're going to use, you can't get lower than this, is shared memory. And we're going to allocate shared memory between two processes where you can both read and write that same memory. That's how we're going to do it. So what I'll do first is we'll go back to PowerPoint, and I'll show you how we're going to do this. So that's the basic architecture. So we're going to design our own remoting channel and proxy. on top. Underneath, we're going to make our own pipe using shared memory. So there'll be an abstract pipe class with an input pipe and output pipe. So here's the requirements now we've got for pipes. We need to be able to send byte arrays to another process. That's it. Send byte array to another process. Has to be, I want it to be extremely low latency, right, for performance. But I don't need high throughput. So I need lots of messages per second. I don't need a lot of megabytes per second. It has to be completely asynchronous because if it crashes for some reason, like your process crashes, I don't want the LINQPad UI to crash. And the fourth requirement, it needs to be bidirectional. But then I thought, well, that's a really silly requirement because that would make it way more complicated. And we can easily create a bidirectional pipe by creating two pipes, one each way, which is what we're going to do. So let's design it. So here's a block of shared memory. So we've got I've nominated the first 5 bytes as a header. 4 bytes represent an integer, 32-bit integer, and this fifth one represents a Boolean value. So the first thing we're going to do, we're going to send a message now into this buffer. We're going to write a message to the buffer. So the message we want to write is 3 bytes long. So I'm going to first length prefix 3 bytes. I'm doing this big endian, but just to make it a little clearer. So the least significant byte comes last. So we write the length prefix, and the message is the bytes 1, 2, 3. We write that. Next thing we do is increment that number at the top. So now that shows we've written a message, and then we flash the interprocess signal. So the other process is reading this. It's waiting on that signal. So it gets that signal. It's going to then read the header. So it's going to go back. It's going to read that header. It's going to see that there's a 1 there, which is greater than what it saw before, which was a 0. So now it's going to read the length prefix 3, and it'll read the 3 bytes. So we'll basically send the message 1, 2, 3 to the other process. Right. The next thing it'll do is it'll go back and read this again and say, is this now 2? No, it's still 1. It'll go back again. It'll spin 1,000 times, waiting for that to go up in case there's a series of messages. Right? Now, if there's nothing else after 1,000 spins, it will wait again on the interprocess signal. Right? Then we want to write another message. We want to write a second one. So what it does is we'll now write a 5-byte message this time. So write the length prefix. We'll write the 5 bytes. We'll increment the header now. So that 1 now will become 2. And we'll flash the interprocess signal. We'll set it. So now we'll keep doing this. The other process will read it. And eventually, we're going to run out of space in that buffer. Right? So at this point, what do we do? Now, you'll notice that what we're doing, there are no locks here. We're not using any locks. Now, normally, if you've got 2 processes or 2 threads sharing memory, you would always use locks to synchronize that. But remember, we want to make this super low latency. So I'm designing this completely lock-free. Right? Now, that means we have to be really careful because when you're doing lock-free stuff, you want to keep it really, really simple because it's so easy to trip up. So one thing we cannot do is reuse that buffer. Not easily, because we need some coordination then with the other process. So what we're going to do is very simple. When we run out of space for the next message, we're going to set up a protocol where we're going to simply create a new buffer. Right? So we'll abandon the old buffer, create a new one. So that buffer had a suffix of .0. The next one will be .1, the next one will be .2. So we always know how to find the next buffer. So all we do, if the message won't fit, is we write 0, 4 zeros in there. That indicates now we've finished with that buffer, we'll go on to the next one. So one more problem that we've got to deal with is that eventually we're going to use up all the memory because we need some way of releasing these buffers. So the process that's reading this, the input pipe that's reading this, see that yellow square in the header? When it's finished reading it, it will set that to 1. And that means now that periodically the other process writing to it keeps track of all these old ones, and when it sees that that's changed to 1, it knows that the other process is finished with it, so it can release the buffer. When both processes release the buffer, then Windows will release the shared memory. Sounds simple? So the next thing we'll do is we'll write that. So the first, what I'll do is I'll show you how shared memory works first, how you access it, because .NET's actually got a wrapper for this, an API. So what you do is you use this static method createNew to create a shared memory buffer with 1,000 bytes, give it a name. And if two processes create one with the same name, they can talk to each other. So this creates called a view accessor, which lets us read and write to it. So what that does, it writes at the 500th index, it writes the byte 123. So let's run that now. And then another process, what we'll do is we'll do the same thing. We'll create one with the same name. And now we'll read. We'll put read int 32 at the 500th offset. So we should get 123 if this works, which it does. Right? Now, the only problem with doing it like that is it's really slow. To do it fast, we need to use pointers, is where the pointers come in. So this is how I would go back to the first one and stop that. This is how I would do that. This with pointers. Instead of using this write method, which is slow, what we can do is get a pointer. And here we are. You call accessor.safe memory map view handle dangerous get handle to pointer. That incantation gives you a void star, a pointer to the unknown. So we can cast that to a pointer to anything we like. So I'm first casting it to a byte pointer, and then we can do pointer arithmetic. By adding 500, we're jumping 500 bytes ahead. Then I can cast it to an int pointer, so now I can write an integer, the 123. So that'll write 4 bytes, 123, 0, 0, 0. It will be little endian. And so we'll run that, and I'll go back to the one that reads it. This one still does it the slow way, and you can see that still works. So that's the basics on using shared memory. So let's go ahead and write the pipe now. So here's the pipe. Now, the first thing we need to do is I've written a class called safe disposable, because one thing you need to be really careful of with pointers is not getting dangling pointers. Dangling pointer is when you release the underlying memory resource by disposing your object, and you still got a copy of that pointer around. If you write to that pointer, you'll crash the process. The problem is it can be very, very hard to diagnose that kind of bug, because sometimes it doesn't show up till later. So we're going to, there's a lot of different ways of doing this with various degrees of robustness, but I've chosen a nice compromise, which is this safe disposable class. It's a fairly simple way of making it much more reliable. Not 100%, but more reliable. So we have a public object dispose lock. So we're always going to lock around this object whenever we access the pointer. And I've got a dispose method, again, which locks around that and calls a dispose call, which is the one we'll override. And I've got an assert safe method, which locks it and says, if I'm disposed, throw an object disposed exception. So the pattern to use it is you'll obtain that dispose lock, and you'll call assert safe. And at that point, you will know that that buffer, that pointer is safe to use. So that's the first thing we do. Now, next thing is I've created a wrapper for the memory mapped file, which is the shared memory. It's called memory map file without a file. Right, so there are fields for the file, for the accessor, and the pointer, which I'm also buffering. Now, this is the constructor, so we're setting all this up. The dispose call, we clear all those things, we dispose them. Fairly straightforward. So this is the abstract now base class for the pipe. So what I'm doing is creating that's the minimum buffer size. So what we'll do is you can make this the size of the buffer dynamic, so it can look at the history of how big the buffers were in the past and automatically size it, which is what I've done in LINQPad. This one's a little bit simpler. So it just comes up with a fairly simple heuristic for working out the length of the buffer. That's the interprocess signal. And this is where we create it. We create the buffer. So one of the parties, right, both of them open the buffer. One creates it, and then the other connects to the existing buffer. That's the suffix of .0 for the first buffer. The second one's a .1, then it's a .2, and so on. We create the event wait handle. That's a signal. So that's pretty much it for the common base class. So we'll look at the output pipe now. we keep a list of all of the old buffers, right? These are the ones that haven't yet been read. And this is how we write a byte array out. We lock that dispose, lock assert safe, protect against dangling pointers, and then we see if there's enough space to write that message. If there's not, we do a continuation, we create the new buffer. Otherwise, write the message and signal the cross-process signal. So this is how we write the message now. This is where we get into the pointers. All right, so we do the pointer arithmetic to take the running offset, add that to the pointer. We cast it to an int star, and then we write in the message length, the length prefix. And this is how you do a low-level blit, right, in the CLR. This does a low-level memory blit very, very fast, much faster than doing it using the view accessor. Does it with pointers. And then we write the latest message number to the start of the buffer. That's to that blue bit at the top. So this bit here assumes we don't have enough space to do it, so it allocates a new buffer in there. It writes a 0 message to the old one to indicate it's not there anymore. And it also adds the old buffer to that list so that we can monitor it to make sure we don't delete it before it's been read. And that cleans up the old buffers. That one reads that Boolean flag and says if that's set to 1, then we're going to remove and dispose that old buffer. So let's look at the input pipe now at the other end. So this is asynchronous. So it runs it on another thread. And what we're doing is the constructor takes an action of byte array. So this tells it what to do whenever it receives a message. It's kind of like an event, but a lot less verbose than an event. Right? You could also do this with an iObservable. So here's the loop. It sets spin cycles to 0, does a while true, gets the latest message ID, reads the message ID, again locks the dispose lock. And if everything's good, it takes the pointer to the buffer and then casts it to an int star and dereferences it. So that reads that blue header, that number there. It reads that number, and then we look, is this greater than the last message ID? So if it's greater than the last one received, then we then read that message. Okay, I'll tell you what this does in a moment. So then if we've got a non-zero length message, it will then call that function on messages like the event. So fire that event whenever we get that message. And then it sets the spin cycles to spin 1,000 times. So we're going to, and the reason we do this is that there's an overhead on waiting on an interprocess wait handle. Right? Interprocess signals are way, way, way slower than ones you use inside your application. So for instance, a lock as well. A lock that you use in C# is very quick, whereas an interprocess lock, a mutex, very slow. So signal's not quite as bad, but we still want to avoid using it if we can. So that's why we spin 1,000 times. So if the spin cycles gets down to 0, well then only then do we wait on that interprocess signal. Otherwise, we decrement the spin cycles. So that's pretty much the interesting part of the pipe. So the only other thing I need to point out is that because we're doing a lock-free implementation, we've got to be really careful because the way that most computers work nowadays with processors is they do lots of really cool optimizations to make things run faster, take advantage of the fact you have multiple calls. And one of the things it can do is it can literally reorder reads. Right, so that means that we could run into trouble. We could end up reading stale data. So there's 2 places that we need to put a memory barrier in here. It's basically it's that optimization where we're reading the so it's in here where we're finished reading go back a bit. We're finished reading a message, and now we go straight back and check that header again to see if there's another message. We spin, right? At that point there, we need a memory barrier to ensure that the reads can't be reordered around that point. So we don't read the header. The read to the header and the read to the data block aren't switched around. So that's why we've got two memory barriers, one in here and one in here. So that makes our lock-free implementation now safe. So let's test it now and see how it works. So first thing I'll do is run a demo. And in this demo, we'll create a new pipe called test and a number after it. Create an input and an output pipe with the same name. And I'm telling the input pipe, whenever you receive a message, I want you to dump the message out. That's what that does. And then I'm going to write two messages, the numbers 1, 2, 3, and then the numbers 1 to 5. So run that now. And there it is. They come through. The numbers 1, 2, 3, the numbers 1, 2, 3, 4, 5. So that's fine. That works in a simple case. Let's run a more rigorous stress test. This stress test now sends a constant stream of messages between 20 and 100 bytes long, which is how LINQPad will be using it. So we're going to now get rid of that, run the stress test. And this now, it does a comparison to make sure that the messages are identical on both ends. So we're getting now 140,000 messages per second, but most of the overhead there is actually in just testing to make sure the message is correctly transmitted and sent. So what we want to do is we'll get rid of the test. So what I'm going to do is get rid of here where we're creating a hash. Let's get rid of that and get rid of this. So we'll just assume it succeeds. That's stress test receive, stress test send. Again, I'm going to get rid of the hash there. Yeah, so let's run this now. And now we're getting 500 and almost 600,000 messages per second on the laptop. So we've got very low overhead, very low per message overhead doing this by virtue of being lock-free. So we've done it. We've created our own pipes in just a few pages of code. So the next challenge is to create the top level. We need to create a channel and a proxy. So what this is, remember, we want to be able to not just send bytes to another process. I want to call methods. I want to instantiate objects in another process and call methods on the other process. So just like you can with remoting. So we're going to do that by creating a channel. I'm going to call it fast channel. And that we're going to create proxies. A proxy of T is the way that we're going to do the remoting. That's a proxy for the remote object we want to access. So these are the requirements. I want client activation. Right? That's a really, really good feature of remoting that I was the only person that liked. Right? So it used to be considered a dirty word, client activation, client-activated objects in remoting. The reason is that people were using remoting mostly for things like web services, right? For loosely coupled applications, you've got thousands of clients talking to a server. You want to scale to thousands of clients. Now, in that situation, client activation is inappropriate. This situation is absolutely perfect for a tightly coupled system, same assemblies on both ends. So what is client activation? It's that the one process will instantiate an object in another process, and that object will stay alive as long as either process has a reference to it. When both processes drop the reference, then it gets GC'd, right? Now, the reason it can go wrong is if one of the processes crashes. Right, the process that's sponsoring it crashes, it's going to stay alive potentially forever on the other process. And they came up with some really complicated, nasty ways of dealing with this in remoting. But we won't have this problem because in LINQPad, if the process crashes, what we're going to do is we're going to scope all of the proxies to the channel itself. Right? We're not going to be static. They're going to be an instance of the channel. So all we do is we recreate a new channel, new process, new channel, and all of those old proxies die with the channel. Right? We don't have to code anything at all. It's all automatic. So client activation will work brilliantly as long as we scope the proxies to the channel. Now we need to call methods with parameters and get a return value back. We're not going to support refs and outs. That's way too complicated. We're not going to let you create generic types. And we do need to support complex types. I do want to be able to serialize complex types. I want exceptions to be propagated transparently. Again, that's quite easy because an exception is just a return value that you throw. I want it to be absolutely fully asynchronous. And I want automatic marshalling and unmarshalling, right? That's a really cool feature of remoting. So what that is, if I'm calling a method in another process, I can pass a reference to an object in my process, right? And then the other process can call methods on that, and it will automatically call back to my process, right? That's automatic marshalling. It's really cool. And then even more cool is unmarshalling, right? So then you can send an object from your domain to the other domain, and then it can send that object back to you, and then you can call methods on that. But it realizes that that's a reference to an object on another domain, which is a reference back to your domain, so to automatically unwrap it to a local object. Right, that's unmarshalling. So I thought it would be really cool. It's not essential, but if I get that working, it's going to make it really, really smooth to use. I want it really super fast. I need to write it in less than a week. So there's some things that kind of contradict each other there, like being able to be fast and being able to serialize complex types. I don't have the time to write a full serialization engine. That's going to take a year to do that. So I've come up with a really good way to compromise on that, though. So let's start with it. So what the first challenge we've got is in being able to call a method in another domain. What does that look like in the code? Like, one way to do it is we could just describe the method and the object we want to call in a string, and all the parameters in a string. But that's incredibly error-prone and clumsy. But in C#, there's a much nicer way we can do this. So in this example, I've got a method foo, which takes an action. It's a delegate. So we can call foo with a bit of code. I can say, foo, I want you to execute console.writeline hello world. Right? And when we call this, it's going to execute hello world, writeline hello world. Right? So that's how we can use a delegate for indirection. But we can change that action into an expression of action. And now that's slightly different. So instead of now getting a delegate, C# builds us an expression tree which describes this code. So this now, A is now a description of that code there. So when I dump out that A, that expression of action, what I get is a description saying this is a lambda expression. The body of it is writeline hello world. It's a method call, and these are the arguments to that. So this allows us to, this is really powerful. So we can expand this a bit. So what I'm doing now is saying if a.body.notype is a call, a method call, then cast it to a method call expression, dump out the method, and dump out the arguments. So I'll run that now. And now we've got, here we are, that's the console write line, and now that's the parameter hello world in there. So this is the basis we can use for being able to execute something in another domain. So let's just flesh that out a little bit more. So what it looks like now when we're invoking the remote method. So I'm going to create a class called fastChannel. That manages the communication, give it a name. And then we're going to have this class called proxy, which is a generic class of remote class. Remote class is an example of a class that we want to remote. So here it is. This is the class I want to instantiate on another domain. And I've got a method called some remote method I want to call, which takes an int and string. So I call channel.activate, right? That's the method I'm going to use to create an object in the other domain. So I want you to instantiate an instance of remote class in the other domain. And then I want you to run on that remote domain, on that object, some remote method with these parameters. So this is the shell of what we're doing. So the fast channel will have two pipes, input-output pipes. That's bidirectional. That's the method to do the activation. So it will create a new proxy for us, which is the handle we can use to call methods on it. And then we need to write code to serialize that instantiation, to describe that we want to instantiate the object and send it to the out pipe. So let's have a look again in that proxy. We need to write a run method in there. So that run method will take an expression of action of tRemote. So this describes the remote method that we want to run. So we'll say if it's not an expression call, we'll just throw an exception saying, I don't know how to do that. So we're only going to allow you to call simple methods. I'm also going to allow you to get properties as well. We won't allow set properties. We won't allow other things like, custom operators and things like that. So now we can dump out the method and dump out the arguments. And then the other thing we would need to do is to serialize that method call into some payload, binary payload, and then send it down the wire. So that's pretty much what we need. And I can run that now. And it should just get as far as just describing this is what we're trying to do. We're trying to run this remote method with these arguments. So here we are running that from some remote method, int32 string s. And these are the arguments we passed in. So we're already halfway there, really, right? A few more things we need. One is we need not just a run, but an eval. We need to be able to call a method and get a return value back. That's very, very similar to what we already did in there. So except that we now have a tResult as well. We have a tResult, eval tResult, and the type is an expression of a func of tRemote, tResult. So it takes the tRemote, that's the object on the other domain, and the tResult is the return value we get from that. The other thing we need to do is we need to provide an asynchronous version of that, because I want to be able to call asynchronous methods on the remote domain as well. So asynchronous methods return a task. All right, so here's what the signature will look like. This mouse is not very good on this surface. So here we are. So it would, instead of taking a tResult, it would take a task of tResult. That's the return type. And it returns a task of tResult. That's going to require a little bit more wiring up. It's not synchronous, so it has to keep track of that remote method when it's complete and send the result back. So as it turns out, when we actually implement this one here, the synchronous one, will also return a task of tResult. Even the activate method will return a task. Everything will return a task. The reason for this is it's possible that the remote process has crashed, in which case even synchronous methods will never return. I don't want LINQPad UI to crash and to freeze because a query process has crashed. So I'm actually going to make everything return tasks. So we can now go to the actual program. So we'll go now to the fast channel. This is all of the code. Now, by the way, if you want to download this code, go to LINQPad samples and hit download, import more samples. And if you go right to the end, here are the samples for NDC Sydney. So if you have understood absolutely nothing in here, you can download the sample. I've stripped everything I possibly can out of it that isn't essential for this. So it's simple enough that you can sort of figure out how it works, and you can hack it and change it, and you can use this as a basis for any other communications library you want to write. Very high-speed communications library between processes. So I'm going to run through it now, how it works. This is a little bit bigger than the last one. So that's the demo. I'm going to look first at the fast channel itself. And things I'm going to point out here is, here are all the proxies. These are the client-activated objects, so we need to keep track of them in a dictionary. Right? This is not a static dictionary, it's an instance of the proxy, so that we avoid the memory leaks by doing that. So that's the dictionary, and this dictionary is whenever we send a message to the other domain, we need to get a response at some point. So we need to keep track of what to do when we get a response. If I call a method on the other domain, it's going to send a return value or an exception at some point. So what do I do when I get the return message? So the way we do this is every message has a number. We keep incrementing the number It's a unique number. So what I do is I create a dictionary, and the key is the number of the message, and this tells it what to do, right? So rather than putting the information in there, what I'm putting in is I can actually put the code, and I can say, do this when you get the reply, in pending replies. So these are the different kinds of messages, all right? The activation means instantiating an object on the other domain. Deactivation is when the GC catches up with it and we want to pass that message on. Method call, simple method call, that's the return value from a method, and that's the return exception, so if the method that you called through. Those are the only kinds of messages. So we start by creating the two pipes. Right, so this is bidirectional, so there's one in pipe, one out pipe. And let's have a look at the send message. That's probably the activate. Here's how we do an activation. So how you activate or instantiate a message on the other domain. So this increments the message number. And then to serialize that, to describe the activation, I'm using a memory stream with a binary writer. That's quite a fast way of doing it. So we can just write some bytes, series of bytes in there. The first thing we do is we write the kind of message, which is an activation. And then we write the message number. And then we need to write the type of the object that we want to instantiate. So I've got a method called serializeType, which does that. And we'll look at that later. Flush the writer. And now we're going to have to wait until we get a response. Right? So what we do is we call this method here, getResponseFuture. That returns a task, right, which we return to the caller. So we'll have a look at getResponseFuture. All right, so what this does, it creates a task completion source, which lets us drive a task, and then it locks that pending replies. Right? That's that dictionary that contains integer, comma, delegate, right? So one of the things that you do when you start getting more comfortable with functional styles of programming is you're willing to use functions pretty much everywhere you would use objects. So we use objects in lists and dictionaries, so why not use functions in lists and dictionaries? So this is a dictionary that contains int, comma, function. So this pending replies, so we're adding to that, we're saying, when we see a reply with that message number, run this code here, right? And it's fairly simple what's in here. There's two kinds of things we're going to get back. It's either going to give us a return value, in which case we just set the result to that value of the task, or it's going to give us a fault, an exception, in which case we need to throw that exception by calling setException in here. Right? This code above here, this preserves the stack trace. Right, that's a little trick you can do to preserve the stack trace, the original one. So it looks like it was thrown locally. Now, the other thing what I did was serialize we needed to serialize the type. So how do we serialize the type? Okay, this is, again, fairly simple. There's two paths, a fast path and a slow path. So this is a slow path, where this will work for anything. It writes either 1 or 2, 1 for fast, 2 for slow. The slow one, it simply writes out the fully qualified name of the type. Very simple. This is it's about that long, right? Puts the assembly name and then comma and the full type name. But I want it to be really fast. So what I've said as a compromise is we can nominate one assembly as being the assembly which contains all the types I want to serialize really fast. That works for LINQPad. There's only one assembly that contains everything that I need that fast serialization on. So if it happens to be that assembly, then I call the metadata token. That's integer. And as long as the assembly is identical on both sides, that's a really fast way to communicate which particular type you want to activate. So we can activate objects now. So the other thing I'm going to look at now is how we call methods. So let's have a look at that. So we'll go to there'll be a method on here to send method call. Here it is. So this is a send method call. Let's find that. Why can't I? Did I close it? No. Oh, yeah, it's too early in the day for me. Okay. Here we are, send method call. So if we do the normal thing of getting the lock and asserting safe, we get the unique message number, we serialize the method call, and get a response future. So pretty simple, really. So let's have a look at what's in there, because that's the interesting stuff, is the serialized method call. So in here, this is where this is the expression tree that we need to serialize. So we look to see whether this is a method call expression, because there's really only two ones that we're going to serialize: a method call or a simple property get accessor. So that extracts the method and the arguments from the method call expression, and this one here gets the details, that the method from the property that we want to get. Otherwise, there's only method calls and property reads can be serialized. Now, this is what the message looks like. We first write a byte to indicate that it's a method call, then write the message number. Then we write the object ID. So I'll look into this in a moment. So every proxy, again, has a number. We keep incrementing for all the proxies. So we have a proxy, a number to identify the proxy. This indicates whether it's asynchronous or not, the method we're calling. Then we serialize the method and then the arguments. Okay, so we'll look at serializing the method first. Again, that's the fast path, right? If it's the recognized assembly, it will just write the method data token. Otherwise, it writes the assembly qualified name and then the metadata token. Now, we'll go back and look at how you serialize the arguments, right? Because this is a challenging thing. We need to be able to serialize absolutely anything, and it needs to be really quick, right? So I came up with a really easy way to do this. So we serialize each one in turn, serialize value. And what we do is we check, is it null, is it bool, is it byte, is it char? So we have, these are the types I need to be able to serialize really quickly for LINQPad, simple types. And we can obviously add to that list if you want. But these are the simple types, so we have a fast path. If it happens to be a simple type, we're just going to do this very simple code, write out the type code, and then we'll write the object out using binary writer. Simple and fast. But the thing is, what if it's a complicated object, complex object? How do we do that? Well, what we do down here is we use the binary serialization engine. We thunk down to that. Now, that's kind of slow, but it doesn't matter, because what I do is it's very simple. If I need performance, I'll make sure all the parameters are simple types. But if I happen to need a rich object serialized and performance is not critical, then it still works. So we get the flexibility and we get performance. You don't get the both at the same time, but that's not really a problem. It's very easy to work around that. So the only other thing we need to be able to serialize are proxies. So remember when I talked about automatic marshalling and unmarshalling? It's one of those things that's easier to code than describe. So this is the code to automatically marshal, and this is the code to automatically unmarshal. So it's really not too bad. It's probably easier to write than describe. So that's pretty much it for the interesting stuff. I should probably look at do the proxies as well. There's a few more things that we need. So with these proxies, because they automatically unmarshal, it's possible that a proxy might actually refer to an object in your own domain. So then you need to be able to invoke that as well. So again, I've got a fast path for doing that. So this is the fast eval. And so I check, is it a very simple kind of method call? I've got a shortcut for doing that. Otherwise, I call the invoke method on the reflection object, which is a bit slower. So with that, let's, I think that's enough showing of code now, because we'll go cross-eyed soon for 9 in the morning. So we're going to demo it now. So here's the demo. I've got demo server and demo client. So the demo server sets up a fast channel, name of test, true, so it owns it. And demo client sets up a channel with the same name. It's not the owner. So this is the one party is the owner, which creates the buffers, and the other one's not the owner, but they're both client-server, really. There's no such thing as client-server because it's really peer-to-peer. They can call each other. So we're going to await channel.activate foo. So we're going to instantiate a remote object called foo on the other domain, and this is the remote object we're going to instantiate. We've got a property to get the process ID. We've got an add method, adds two numbers together, and an asynchronous version of that awaits for a second and then adds the numbers together. So we're going to demo that. So first we'll activate the foo object. We're going to ask for its process ID, and then we're going to add two numbers together. I'm going to call the remote add method foo add 2 and 2, and then I'm going to do the async version of that. Right, you notice they both return tasks. They're both async, so we have to await each of them, and then we'll run that. Now, one thing I want to point out is that this is actually pretty much ideal when it comes to the extra ceremony we've got in here, because in order to call the remote method, we have to add this extra stuff here onto there. Rather than just calling foo.add, I've got to put await foo proxy.eval foo fat error. That's a bit of extra clutter, but it's extremely welcome clutter, because I remember the problem I had with remoting, which was where there's no clutter at all, is it's so transparent you don't know whether you're remoting or you're localing. Right? And I've had problems accidental remoting. Right, where I thought I was localing and I'm actually remoting. With this, it can't happen. This is really important because this tells you everywhere in your program where there is a potential remote method call where you're crossing a boundary. And so this is actually a blessing to have this bit of extra clutter in here. Let's run this now, see what we get. And it works. The remote process ID is same as our process ID because we're running on the same process at the moment. The sum, we're adding 2 and 2 together. And then 3 and 3 together, that all works. So, and that's the code that's running on the other end, the other process ID. So to really test this properly, we kind of need to run it in separate processes. So let's clone this a couple of times. So the first clone, I'm going to just demo the demo server. In fact, all we need to do is put a console.read line in here. Let's do that. So that's going to run the server. And then in the other process now, we're going to demo the client. And here we are. So that all works in the same way now. So it's running now on a different process ID. All right, foo's process. So we've got 2 process IDs happening now. That's all good. That all works. And final thing I want to show you is the automatic marshalling and unmarshalling in there. So now I've created not just a foo, but a bar as well, right? So we've got class foo, and we've got class bar. All right, so the bar class has a method that returns a foo proxy. Right? This is automatic marshalling. So all we need to do is put new foo in here, and it will automatically convert it to a proxy of foo to marshal it for us. And I've got a print foo method, takes a proxy of foo. And we can call these methods seamlessly now using this, here it is, marshalling. So I'm going to activate now a bar, and then I'm going to call the method on the bar to get a foo. So I'm going to end up with another foo proxy. And then I'm going to call the add method on there. All right, so we're going to go back to ourselves. So let's run all that and make sure that runs too. Automatic marshalling and unmarshalling, and that all works fine. Yep, that's that code here. So that all works fine. So here it is. So you've got all the code, you can download it, and it's not too big and complicated. And hopefully I haven't scared you too much for a 9 a.m. talk. So any questions on that?
What kind of performance improvement did you see? Like, what is the magnitude between seeing out and stuff?
Okay, the performance improvement was over remoting. It was several times, somewhere 5 to 10 times faster in terms of latency, which is the one I wanted. So I programmed entirely. I wasn't trying to make it fast throughput. I was trying to make fast latency. And I got 5 to 10 times because of that underlying lock-free pipe that I'm using, and the fact that there's a fast path in the remote encode. But simple scenarios.
Why bother having, if you're always returning a task, why bother having a synchronous version at all?
Because the difference is between the synchronous and the async is that you still need to be able to call there's a difference between calling a synchronous method on the remote end and an asynchronous method on the remote end. So the async method, it has to handle the reply differently. So at the remote end, the synchronous one, it will get the reply straight away, whereas the async one, it will come back when the task completes.
Just for the pipe, is there a reason you destroy the memory instead of reusing it after it's done?
Okay, that's a very good question. So what you're suggesting is that you could like have a pool of yes, you definitely could. So if you were very careful on how you coded it, the lock-free stuff would make that challenging, but you could certainly have a pool of buffers that you recycle. And that was something I thought about. But because the design criteria was for low latency and not high throughput, that wasn't a design criteria. So I never got around to doing that because it wasn't necessary for the performance criteria. But if it was, if you wanted high throughput as well, then that would be an excellent way to go, is look at a strategy for recycling the buffers rather than creating new ones all the time. Okay, well, that's all the questions. So thank you all for coming.